Good morning. So, today I will discuss about another energy device or energy generation process, which is thermionic energy, and we will see the thermionic energy related materials and the devices. So, in the previous lecture we have seen that heat energy can be used to generate electricity, and what we have seen that thermoelectric generator is a device where heat energy is used to generate electricity. So, in thermoelectric generator, what is done essentially that there are two junctions which are created. One is hot junction, another is cold junction, and a temperature difference is maintained between these two junctions, and when there is a temperature difference, then there is a EMF developed, and this EMF is actually an electrical energy. And what we have seen that if we make a thermoelectric generator or thermoelectric device, we use semiconductor, N type and P type semiconductor, and make a special device architecture, and we generate electrical power. So, the quantity which control this process is figure of merit, which is in the other way depends on Seebeck effect or Seebeck coefficient, electrical conductivity and thermal conductivity, and eventually what is known as figure of merit. And then from there we have seen that what is the efficiency of a thermoelectric generator or thermoelectric device, and then also how much power this generator or this device can deliver. So, this is a solid state energy generation device, and which I mentioned in various applications that this is a compact energy generation source, and which we can use from spacecraft to biological organism, depending upon how much heat we can generate and how much temperature difference we can maintain in the two junctions. Side by side, another heat energy related an electrical energy generation process was also developed, and that is thermionic energy. So, in this case again the heat energy is used, but in this case an EMF is not developed by keeping these two junctions at two different temperature, but what is done that one particular electrode is maintained at high temperature, and this is known as emitter, and then another electrode is maintained at cold temperature, this is a collector. So, whenever this emitter is heated, it generates electron, and these electron they go towards collector, and then they go through an outer circuit where a load is connected, and then a voltage is developed across this load. Okay, so, it generates voltage or it generates electrical energy or electrical power across the load, and this particular process depends on how efficiently this emitter can emit electrons, and of course, how efficiently the collector can collect the electrons and then pass it through the outer circuit. So, this is a typical electrical energy generation process which people have started studying for quite some time, and they realized that such energy generation process would be very much useful in spacecraft, and also for terrestrial use. But for quite some time, this particular process was not considered as a potential process to generate electricity as far as the large electricity is concerned or large power generation is concerned. Although there are a lot of promises, but now with the advancement of materials and also the technology associated with this energy generation process, the research is pushed towards the cutting edge, and people are realizing that thermionic generator can be used as a very potential source of electrical energy or electrical power. Okay, so let me just go to little early days. We remember that in our school time we used to study the cathode rays. So, what are cathode rays? A cathode rays is that inside a sealed tube with a little bit of vacuum or low pressure inside the sealed tube, a metal electrode is a voltage is applied to a metal electrode and it emits a ray which is cathode ray. And people have seen there are a lot of experiments which people are doing with cathode ray, and particularly the pioneer of this experiment is Sir J.J. Thomson. And then one can see a glow if this cathode ray strikes a glass coated with certain phosphor material or light generation material. So, one can also put a metallic cross something like here this, and then one can get a shadow of this cross. That means this part, the ray which is cathode ray, is what Thomson realized that it definitely consists of some particles. So, this was a time when the people started studying about atom and atomic structure, and also the Michael Faraday gave an idea that atom is possible which is neutral, and then one can have ion, positive ion or negative ion. Suppose if I consider NaCl, then Na plus is a positive ion and Cl minus is a negative ion. So, those ideas were there, and people were thinking that this cathode ray, what sort of particle flow is there in the cathode ray? Is it the atoms which are moving? Then what J.J. Thomson did, he also elaborated this experiment with magnetic field, electric field, and tried to see that whether this particle can be reflected or some sort of force can be generated on that. And finally, he came out with a very clear idea that this cathode ray basically consists of a fundamental particle, and this fundamental particle which is smaller than atom, and this particle has negative charge, and these are actually electrons. And the mass of these particles are much less as compared to the mass of atom. So, before that people have idea that the atom is a fundamental particle, but with this great discovery of Thomson, it was realized that atom also consists of other particle, and electron is a particle which is more fundamental and it is of negative charge and mass which is much less as compared to atom. And now we know that one electron has mass almost 1000 times less than proton, neutron, etc. Now, this was the discovery of electron, and then Thomas Alva Edison, he was working with this generation of light, and then he realized that if we can have a metallic filament, and if we heat this filament, then the electrons can come out from this filament. Okay, this is what his idea was. It's completely experimental, and later a theory was developed for this, and that means the electron generation by heat or providing heat to a filament. Okay. And then if we have a configuration something like this, where we can have a filament which can be heated by a voltage source, okay, and then there is an anode. So, from here electrons are generated, they are collected in another electrode, and then an emitter is connected in this path. Okay. Now, one can apply a voltage source here with positive and negative potential in these sides. So, that means the particles which are coming in this direction, they are attracted by the positive plate of the battery. Okay. So, that means these particles are definitely negatively charged, and now people had no confusion that these particles must be electrons, they are negatively charged, they show a very clear current in the emitter. Okay. So, now you reverse this potential, that means you connect negative here with this electrode and positive in other side, then there is no current. Okay. So, this particular experiment actually triggered a complete technology in electronics, which is known as vacuum electronics. And presently people do not know about vacuum electronics, but I think 20-30 years before it was in the textbook that vacuum diode, triode, etc., and we used to study about this and how one can make diode, triode, which are completely based on this electron emission process by temperature or by heat. So, these are typical examples of thermionic emission. Okay. So, we go little more this historical perspective of the thermionic emission, how this chronologically it is the subject is developed. So, going back to 1733, where C. du Fay shows the conduction of electricity in gases. Okay, this is the way people have started working. Becquerel showed that electric current through air between platinum electrode, and Kirchhoff, actually this was a discovery of cesium, and then the breakthrough came after the discovery of Thomas Alva Edison. So, what he has seen that he discovered the thermionic emission, which is our topic here, and what happens that electric current flows, as I have shown that if you have a sealed vacuum tube and one side you have a heated filament or heated electrode, then the electron flows between the electrodes and it generates a current. Okay. This current can be controlled by another battery or field applied outside. All right. And then during this time around 1882 to 1889, Astor and Gretel, they have shown the electrical effects of incandescent solids sealed device with hot and cold electrode. So, these are actually a further work on these vacuum tube based thermionic devices. And then again this was a breakthrough in 1897, as I mentioned, that Sir J. J. Thomson describes nature of electron. It was a fundamental experimental study, and then another breakthrough came in 1915, where Schlichter actually used this thermionic emission properly and showed that how electricity can be generated with this process, okay, or the energy can be generated through this process. So, a conversion of heat energy to electrical energy was first, the idea was shown at 1915 by W. Schlichter. And then again there was a famous theoretical work which was done by O. W. Richardson. He gave the theory of thermionic emission and showed what are the material properties is required for a good thermionic emission process. We will come to this particular theoretical work which Richardson did. Okay. And there is some theoretical work which was done by Langmuir also, because when the electrons are generated and they are flowing from one electrode to another electrode, it happens that sometimes the electrons are actually captured in the space itself, generating some space charge and hinder the further flow of electron, which is known as space charge effect. So, Langmuir did theoretical work on this space charge effect, and in 1956 the thermionic heat to electricity conversion was demonstrated. Okay. Of course, there are some study related to thermodynamics, but the real use came when NASA in the spacecraft they use these thermionic devices, and also in Russia they use that Topaz 5 kilowatt reactor. Now, why people were so much excited? Okay. The reason behind this is that, as I mentioned, during this thermoelectric generation device also, that there are a lot of waste heat. Okay. So, this heat can be a small amount of heat that we have seen that one can use a thermoelectric generator in pacemaker. So, where we have this heat generated from the body and this can be used in generation of EMF. Okay. Or there may be a large amount of heat generated somewhere. So, suppose in the fossil fuel or in the nuclear reactor, all right, or the solar heat. These are the heat which you can think about, it is a huge amount of heat which are getting wasted. Okay. So, this heat can be used, and then by the thermionic process one can generate electricity with the heat. So, entire excitement was there, but as I mentioned that for quite some time, for few decades, people could not use it for electricity generation, or they show that the efficiency was not that high. But now again the research has developed many materials including nanomaterials, which we will discuss later, that what is the progress of thermionic material and thermionic devices, which again bring this research a potential research for energy generation. Now, I come to some general application, some application which we still see in our laboratory, and also of course, that I do not know nowadays people do not have this television set at home, because most of the TV sets are all with LED displays. Okay, but earlier the display of the television was not based on LED, they are based on this thermionic source. So, there used to be a small electron source. Inside that there used to be a very high voltage generation in that using a step up transformer, and then these electrons used to go and deflected in electric fields or the plates which electrical plates were attached to that vertical horizontal sweep of the electron, and they used to strike in a phosphor plate which is actually the screen of the TV, and then they used to scan this electron and used to generate all the the pictures. But this technology is not seen nowadays, but it was there for quite some time. So, this was actually a application of what is known as vacuum tubes for electronics. Okay. So, I already mentioned that vacuum tubes for electronics were used in diode, triode, etc., pentode, etc., and there used to be a vacuum electronics, and it was there for quite some time in research as well as in the practical application. But now these things are all replaced by the solid state electronics, diode, transistor, etc. But still we see this cathode ray tubes for display. This you can see in the laboratory. So, student uses cathode ray display, and what the cathode ray display, we all know that if we want to see the voltage, we want to see the current. So, you can see exactly in this cathode ray display. Okay. And here actually again the same way as I mentioned this earlier television set, exactly the same way there is an electron source there. It is basically a thermionic electron source, and electrons are being generated, they are scanned by electric field, and the displays are produced. Okay. So, one can also make beautiful Lissajous figure. So, you might have seen in cathode ray tube. Then another very important application was in electron microscope. So, this electron microscope was developed quite some time back, and this electron microscope, they use a small electron source. Okay. These electrons generated from the electron source, they pass through a sample or any material under investigation, and these electrons are focused and intensified by electromagnetic field. Okay. And when they cross this any material which is under study, they actually eventually they are transmitted and they are captured in a photographic plate or nowadays in the CCD camera, and then it can show very small scale structure of the material which in the material which are cannot be seen by general optical microscope. Optical microscope are generally of few micrometer resolution, but in electron microscope you can go down to nanometer resolution, because it works on the principle of electron wave, and the wavelength of electron is very small. But the important point is that this electron source or thermionic electron source was used in the electron microscope, but these days people use field emission electron source. This is another way of generation of electron. We will come to this particular generation also, but our main focus will be thermionic emission. And then X-ray tube. X-ray tube now also, whatever X-ray tube you use either in the laboratory or for any crystallographic study or even for medical X-ray imaging, there is a small electron source there, okay, thermionic electron source, and this electron goes and they strike to another metal, say copper, and then the characteristic X-ray from that particular metal come out. Okay. K alpha, K beta, etc., and these X-rays are analyzed. So, the small electron source has lot of role in making X-ray tube devices. Similarly, microwave generation also these electron sources are used. Here the source is known as klystron source. So, if you are interested, you can study how microwaves are generated in the klystron source, and then electron beam lithography. Okay, we know all this pattern generation, optical lithography, and then electron beam lithography, where an electron beam is generated particularly by this thermionic process, and these days people also use the field emission process. Okay. So, this electron beam can be used for lithographically to generate the pattern or structure of whatever dimension we would like to make. But we will focus mainly to this particular application, which is electrical power generation. So, this particular lecture is dedicated to understand how electrical power generation can take place in a thermionic generator or thermionic converter. But before that, let me just discuss very briefly about what are the electron emission processes. Okay. So, you can imagine this why electrons can be emitted from a material. So, let me take an example of a metal, and we know that in a metal the electrons are filled up to a state which is Fermi level, okay. And then I define another energy level, this is the E vacuum or vacuum energy level, okay. And then this difference between the Fermi level and the vacuum energy level is defined as work function phi or W. This is known as work function of that metal. Work function of this metal generally represented by phi or W. So, now if there is an electron here, an electron is sitting here and we give some heat to this electron, okay. I provide heat and this electron gets energized, and then it crosses the barrier, okay, that is vacuum level, or it goes above this vacuum level. That means, it actually gains energy more than its work function, all right. And then what happened? This electron goes to in free state and we can see a free electron. So, this is typically what is known as thermoionic emission. Okay. One can also, so I write it thermoionic emission. All right. And now I replace this heat okay, by a photon. Then electron gains energy from the photon, and we know that there is an effect called photoelectric effect, which was explained by Albert Einstein, and he told that these photons are basically energy packet of h nu energy, and when they come and fall on electron, they give energy to the electron, electron gains the kinetic energy, and if they can have enough kinetic energy so that they can cross this the potential, or they gain energy more than the work function, okay, then they go to free state. So, this is the second process, which is known as photoelectric emission. Now, I can have another process by which there is no light, no heat, okay. So, what I do here, I apply a high electric field, and then this barrier can be bent or lowered. Then this electron can be quantum mechanically tunneled through this barrier, and then this process is known as field emission process. Okay. So, these are three ways of generation of electron. There is another way of generation of electron, which is known as the secondary electron emission process, where a primary electron beam is used and they actually strike off electron from the material, okay, and these secondary electrons can come out generating secondary electrons, and these secondary electrons are used in microscope like scanning electron microscope or SEM, where the secondary electrons are used. Okay. So, these are the different electron emission process. Out of these three electron emission process, our focus will be the first process, that is thermionic emission. So, I mentioned in this history of this electron and the emission process, the thermionic emission, the theoretical model was given by O.W. Richardson, and he received Nobel Prize also for this discovery. So, where he had shown that J, that is the thermionic electron, the current density due to the thermionic process, okay, is proportional to T square. T square is the temperature which is provided to the thermionic emitter, and it also depends on W, which is the work function of the material. So, it depends on work function of the metal, it depends on the temperature of the surface, okay, and it also depends on the surface area. Okay. So, what is the meaning of surface area? Surface area means if we can increase the surface area, that means if I can engineer the material in such a way that one can increase the surface area, one can have more number of electron emission, and this can be nicely understood from here, that if these electrons are there on the surface and the electrons are getting emitted, if I increase the surface area, the electron emission will be enhanced. Okay. And Ag is a constant which is also known as Richardson constant. Okay. Later people did a little modification of this, where Ag was written as some quantity lambda r into A naught. A naught is basically the Richardson constant, A naught is 4 pi m k square q e by h cube. Dimensionally it is around 120 ampere centimeter per Kelvin square. Okay. And lambda r is basically a quantity. It basically depends on that how electrons are coming out from the surface. Okay. So, this is actually material parameter, because we all know that electrons are also a kind of wave. Okay. And then there is a fraction of electron which can be which can come back. So, now when we make a thermionic energy converter, so what are the things, if we look at the steps how it happens. So, let me again draw this. So, as I told that we have an emitter, we have a collector, and then this is connected with the heat source, and this you can say is cold or heat sink, and then when it is hot, then the electrons comes out from this emitter and they goes towards the collector. Okay. And then if I have a circuit something like this with the load here, R L, then one can generate a potential V across this load, because the electron will again find a path here in the opposite direction. Okay. And this gives a voltage. So, what are these steps? The first step is that you provide heat energy to this configuration, all right. And then second is the thermionic emission, that means the electron emissions take place from the emitter. And third step is electron flow, as I have shown here, this electron is flowing. Remember that I have not shown any space charge effect here, which I mentioned. I will come back to the space charge effect again. And then there is a current generation, which we have seen here, a current generation, and of course heat rejection, which happens to this through the collector. Okay. So, these are the thermionic energy conversion steps. Okay. So, eventually what we have done by this entire process, we actually have generated an electrical energy from heat energy. Okay. So, there are some important points which we have to remember, that when we have done this or we have generated the electrical energy from the heat energy, what are the key points in this? There is a direct energy conversion process. So, we do not have any intermediate steps here. Okay. The heat energy is provided to the emitter emits electron, and then it goes to a collector, and the electrical energy is generated when it comes back through a circuit. Okay. So, this is one key point. Second point is high temperature heat rejection. So, we have also seen that it is used as high temperature, as high as possible, and generally the thermionic generators or thermionic converters use temperature which is more than 100 degrees and 1000 degrees centigrade. Okay. more than 1000 degrees centigrade. All right. So, thermionic energy converters, the temperature is relatively higher as compared to thermoelectric generator, and heat is rejected. So, all the rejected heat from some source like nuclear reactor is used now here to generate the energy. It has high specific power, okay, and also there is a potential for higher efficiency. So, we have to understand what do we mean by efficiency of a thermionic converter and how one can improve the efficiency of thermionic converter. So, first I will discuss a very simple way to understand what is the efficiency of a thermionic converter, or if we make a thermionic the energy generator, how one can estimate the efficiency. The way we have discussed the efficiency calculation for thermoelectric generator, it is in slightly different way, but you know that both thermoelectric generator and thermoionic converter, they are thermodynamic devices, because there is a temperature difference. Okay. So, therefore, if we can consider them as a Carnot cycle or Carnot engine that we have discussed in case of TEG also. So, generally this theoretical efficiency is 1 minus Tc by Te. Okay. C is the temperature of the cold junction and E is the temperature of hot junction. Okay. But we have to look at from the electrical energy point of view. So, if we look at from the electrical energy point of view, one can also derive the efficiency in slightly different way. So, let me show here. So, this is the vacuum level. Okay. This is the vacuum level, and then this is the Fermi level, this is emitter. So, this is Fermi level of the emitter, this is the collector, this is Fermi level of the collector. Okay. So, this is the work function of the emitter and this is the work function of the collector. All right. So, I have to choose the work function of the collector in such a way that there is a difference between the work function of emitter and collector. So, it is always important that we choose the material for collector whose work function is much smaller as compared to the work function of the emitter, and then this is the path RL, and then this amount of voltage or energy is generated, which is proportional to the difference in the work function of the collector and emitter. Okay. So, generally the voltage which you have generated is basically a voltage which is proportional to the difference between the collector emitter work function and the collector work function. Okay. So, now one can also define the efficiency. So, this is a voltage. So, I can write the efficiency, which is the power generated divided by the total heat. Okay. So, there are different components of heat, and I will come to this heat. What are the components of heat? One, heat, we know that there is a heat from the heat source. Okay. There may be some loss of heat also, okay, by radiation or by some other process. So, that we have to take care of this heat loss, and that I will show that when we will discuss about a device configuration. That means it is decided by the current flowing through the circuit, okay, and it depends on the voltage. That means, it depends on the work function difference. When we do this, there is always a space charge effect, because when electron starts travelling from the collector to the emitter, they somewhere near the collector, near the emitter, or in between this, the space between collector and emitter, they can create an electron cloud. Okay. So, let us again look at that the efficiency depends on the emitter and collector material, that I discussed that the difference between the work function should be high. Generally, we choose material of low work function as emitter, like tungsten, okay, or thoriated tungsten. I will come to this material aspect in my next lecture. But now what we can understand, that one material can efficiently emit electron when its work function is low. Okay. Now, another factor is that one should also choose a material for as collector whose work function is even further less as compared to emitter, because you want this difference phi E minus phi C to generate maximum voltage. Okay. So, I also mentioned about inter-electrode spacing. Operating temperature, we have seen from the Richardson equation, this operating temperature is high, T is high, we have higher current density. And now we come to this particular point, space charge effect. So, what is space charge effect? Again, let me just draw it very simply, that this is the emitter, this is the collector, and this is heat. Electrons are emitted, but they can generate a kind of cloud here. Okay. So, the number of electrons which are reaching to the collector is reduced, because many electrons can be repelled back from the space charge. All right. So, this is a very crucial issue in vacuum electronics, and I mentioned that this Childe language gave a detailed theory on that. But what people later realized, that this space charge can be neutralized by putting some sort of vapor of some, say, cesium vapor. Okay. So, this can be neutralized, and electron flow can be this, which was hindered by this space charge, can be reduced. Okay. But when there is a space charge effect, we have to see that how actually it changes the entire potential. So, what will happen in case of space charge? If I again try to draw the potential graph, then what we have seen, that this is the vacuum level and this is the Fermi level of emitter, and collector, this is the Fermi level of collector. So, this is phi E and this is phi C. We can have an extra potential developed here. Or so, this extra potential actually comes from space charge. So, that means due to space charge, electron finds another barrier, and this barrier has to be reduced. So, let me just take few examples. Okay, how one can actually look at one starts engineering the materials or the device. So, you can see that these two cases which I have shown, and this is the extra potential which you see for the space charge, and this is the work function of the emitter, this is the work function of the collector, and as I mentioned, the difference between these two work function is actually the voltage, okay, of the thermionic generator. And now, if we look at these two cases here, you can see the voltage generation is less here as compared to this. Okay. Now, what happened that this voltage generation can be controlled, as I mentioned, by changing this phi E and phi C, and you also have this extra potential due to space charge which I just now I discussed. Okay. So, one can have two different voltage generation by changing this potential energy level, and another way one can the control this particular process, where you can keep this voltage generation in the circuit same in the two cases, but just by changing this potential height here. So, you can have a very high phi E here, and you can have a very low phi E here. So, that means in case of low phi E, you need less heat to be supplied, and for high phi E, you need more heat to be supplied. So, two things which you control here. One is if I vary this work function of the emitter and collector, okay, I can vary the outside voltage whichever is generated in the circuit. In this case, I keep heat exactly same, and now if I change this work function of the emitter, then what we see that for same amount of voltage to be generated in the outside circuit, we need to supply more heat. Okay. So, I will just discuss what are the emission requirements. Okay. So, one particular issue which I have already discussed, that one can change the potential or one can change the supply of heat or vary the heat supply just by changing the work function of the emitter and collector. But apart from that, also there are several requirement of the emission, entire thermionic emission. Okay. So, if I look at the two important requirements for emission are low work function, so that you need to supply less heat, and high Richardson constant. So, that we have seen from the Richardson equation. And what are the emission advantages? There is a very important thing which is known as negative electron affinity. Okay. So, the surface whatever we can make for a better emitter is basically decided by what is the electron affinity of that surface. Okay. What do we mean by this? The meaning is that suppose I take a semiconductor where this is conduction band and this is valence band, okay, and then I have a Fermi level here and I can have a vacuum level here. So, this energy difference is known as phi, that means or work function W, but then I can have another energy level which is known as electron affinity. Which is basically vacuum energy minus the conduction band energy level. So, what do we mean by negative electron affinity surface? It means that if this vacuum level is somewhere here. Okay. The phi or work function is still positive, but I can have a negative electron affinity. So, what happens, this negative electron affinity will help to generate electrons. So, negative electron affinity surface is another very important quantity or important parameter for thermionic emission, and when we will discuss the material issue, we will discuss about the negative electron affinity surface. Another important point is that low thermal radiation emissivity. If there are more thermal radiation, then we lose heat. So, one can also control this radiation, okay, or emissivity, and we will discuss the device design. I will discuss what are the kind of radiation that can take place in a thermionic generator or thermionic converter, and why the low thermal radiation emissivity is required. But when we make a device, there are several requirements related to device. The stability should be high, the current capacity should be high, voltage capability should be high, and we have seen how one can change the voltage capability, and there should be a stable and effective low work function layer. Okay. So, when we design any material or we do research on any material which are used in a thermionic generator, we have to keep all these points in our mind, and also when we make a thermo-ionic energy generator device or converter, we have to keep these points in mind. Okay. So, at this stage, if I summarize today what we have discussed, we started with the basic understanding of electron emission process. After discussing little bit of history of different electron emission process and thermionic electron emission process, and after that we discussed the theoretical understanding of thermionic electron emission by Richardson, and then we have seen that how this voltage is developed in a thermionic electron generation device, okay, or thermionic converter. Okay. In that case, we have seen that the voltage which is being generated is always proportional to the difference between the work function of emitter and the collector. And what we have seen, what are the material requirements, because if we want to generate higher current density, then we need lower work function and higher temperature. However, one can also control this amount of heat supplied or the voltage generated in the circuit just by playing with the work function of the collector and emitter. We also have highlighted the point that the space charge is an important issue and how it creates an extra potential along with this work function. And then what are the emission requirements? In the emission requirements, we have seen several points like work function, low emissivity, stability, and another very important point, that is negative electron affinity surface. So, when we will read or study about the materials in our next lecture, we will see this entire design of the material and the device are basically based on all these fundamental points which you have discussed in this lecture. Thank you.